everyone. My name is Joaquin van Schoren, and today we'll talk about convolutional neural networks. So we'll start by looking what an image convolution actually is and why it's interesting. Then we'll see how we can use it inside convolutional neural networks. Then we'll talk about how we can augment our data to get more of it. And then we'll see how we can interpret whether the model we've trained actually learned something interesting. And we'll finish off by looking at transfer learning to see how we can use previously learned models to learn problems, harder problems, with less data than before. First of all, a convolution. A convolution, or an image convolution, is an operation that transforms an input image, like this handwritten 0, into an output image. We call that a response map. We get that by taking a second smaller image called a filter or a kernel and sliding it over the original input. What we'll do is we take a small patch of equal size as a kernel. This one will also be, in this case, a 3x3 patch. And we'll multiply every element-wise, with our filter, right? So you take this pixel value times this pixel value plus this pixel value times this pixel value plus this pixel value times this pixel value, and this 9 times. Right? The result of this sum will be our output value here. Now in this case, because these are all zeros, multiplying by zeros gives us a 0 here as well. Once this image goes on and hits some non-zero pixel values, you also get a non-zero output here, depending on the filter. Right. So what does this look like? This is, for instance, our horizontal edge detector. So we'll start by making this move over the image. For now, nothing happens because it's just all zeros. Once we start hitting this one, you'll see we actually get some outputs. And we can see that what this filter does, it highlights horizontal edges. If you turn it back a little bit, what we'll see is that it's somewhere here, right? Okay, so we multiply element-wise this patch times this filter, right? And because the patch in the background has a non-zero element here, the +1 here gets a big contribution, while the -1 here has almost no contribution. And this means that the result of this sum is a highly positive output, right? On the other hand, if we move this forward and we go to the next row, we can see that now the value is lower. Why? Because we have some positive value here. We also have a negative value here, which cancels each other out. Right? In that case, we have kind of mediocre value here. And we can continue to do this all the way down. And what we'll see is that this filter activates the top of all horizontal edges. So you get a positive value here. And on the bottom of a horizontal edge, you get a very negative value here. If you do this for the entire image, you will see that what this filter tells us is where the horizontal edges are, where they begin and where they end. Okay. And this is very useful because now we don't have to look at individual pixel values, but we can actually look at things as like, where are the edges of this line? And we can use that as inputs for our classification in the end. And we can do this for different filters. This is a horizontal edge filter, so we see where the horizontal edges are. This is an edge detect filter, so it shows you the beginning and the end of edges. So here we actually have two edges because it's like a kind of fat 0. So you have an edge outside here, and you have another edge on the inside here. And this is our diagonal edge. This kind of highlights more strongly whenever we have this diagonal edging here. All right. Now let's take a look what this does for a real data set. So here we have the Google Street View data. So these are images from Google Street View, which are focused on house numbers, and they're nicely cropped around individual numbers. Like here it's cropped around the 1, here it's cropped around the 9. And you can see that, of course, there are some edge effects like other numbers which are surrounding the number. Not so much here, but here it is very clear. Other images are very noisy because they're taken from far away. Right? So this is not so easy to classify. The first step that we can take is to remove the color, because the color probably has no effect on classifying the numbers. It doesn't matter whether this is a blue one or a red one, or maybe a white one on a green background, right? So for that reason, we remove all the color, which makes the problem a little bit easier. Okay, now we take one of these images like this tree, and we can do the same thing again. We can take this filter, remove it over the image. We see some edge effects here. But overall, we can see that again, we learn where the horizontal edges are in this image. And again, also where the bottoms are. Right? So if we do this for different filters, again, we learn different things. We learn, in this case, where the horizontal edges are, where the edges are, and this is where diagonal edges are, and this is where all the edges of the image are. Okay, so, and the interesting thing here is that we can now represent this data in different ways, which gives us different types of information. And with these different types of information, we can probably learn this problem much better than otherwise. Now the question, of course, is which filters should you use for your specific problem? And to get around that, you can use a family of kernels or a filter bank, like maybe 60 or maybe 100 of these filters, and run them over your image. And many of these families have been defined, like Gobbo filters or Gobbo filters or hair wavelets. And one example, for instance, are Gobbo filters, which is kind of a wave pattern, looks like this. So you can play with the resolution. So we can take a look at the high resolution wave, and then we can change the frequency, like a low frequency here. And we can also change the angle, theta. So we can turn it around whatever we want. And so every combination of these settings gives us a certain filter that we can then run over our image. And so by defining a number of these settings, we can create a filter bank, and then we can run the entire filter bank over image, thus producing many output features. Right? So if you do this for this number 3, we can, for instance, let's take lower. Okay, so this is what I had before, more or less. We can try to increase the sigma value so we get more noisy outputs, or we can make it smaller and then maybe look at different directions. So you can also play with this at home. Yeah, you can see that this is a little better. So here we can again recognize some edges. Let's increase it a little bit. So you can see by playing with these different settings, by these filters, we get different outputs. And here we can see a filter bank. So here we have maybe 8 of these. And we see every filter here has an effect on different numbers. So here we have a 3, here we have a vague 5, here we have a narrow 8, And different filters kind of give us different information about all these images. And so the idea is that you take an input image, you create all these transformations, and you use these as new features, which are hopefully easier to learn from. And then you can give them to any algorithm to learn from. Okay. Will this also work for more realistic images? So here we have our fashion MNIST data. And of course, again, we can try different filters, and these will again respond differently. So we can just change the theta here to look at different kind of edges, like top edges or left edges and so on. Every time we change the filter, we get different outputs, and hopefully we end up with outputs that are useful for making predictions in the end. If you do this for the filter bank, we can see, for instance, this dress. In this case, the vertical lines are highlighted a lot. The neckline is highlighted with the dress, but not with the t-shirt here. We can see the vague outlines of the images without all the noise inside. So these look like interesting representations of the image, which hopefully we can learn from better than from the original images. Now, the idea behind a convolutional neural net is that we want to learn local patterns. So instead of learning the relationship between individual pixels and the output, like number 4, we want to first detect certain local patterns like lines and endpoints and so on. Because if we can detect these things before, that will make it easier to then recognize this image as a 4, right? So we represent this image as a bunch of endpoints and lines, and we hope that by doing that we can recognize this image as a 4. Yeah. Now, again, we can use convolutions, we can use filters to detect all of these edges. But the question again is, how do we choose these filters? So the whole idea behind a convolutional neural net is that instead of manually designing these filters, we learn them based on data. We don't learn them entirely. We still have to choose, for instance, the sizes of the filters. And there's an art to this. But once we chose the size of these filters, we can then initialize them randomly and then learn them based on data. Now, there are some ground rules. For instance, if the input here is a color image, which means it has 3 channels, red, green, and blue, our filter also needs to have 3 channels. We can still choose the width and the height of this filter. In this case, we choose a 3x3 filter, which means that for this color image, we need a 3x3x3 filter. And again, the convolution happens the same way. We take this pixel value times this filter value plus this pixel value times this filter value plus this pixel value plus this. And we take, again, the element-wise sum of all of these corresponding products. We sum them all up, and that's the end result we pass. And that's what we call the feature map or the output tensor. So we take this one, we compute the convolution, and this will give us one output. And then we shift it again, and then we get the second output and so on. Now, in practice, we will not take the raw output. We will first pass the output through an activation function, but we'll come back to that. So how can we now learn these weights? Well, the same way as we always learn them. We take an image, we pass it through these filters, out comes a new output tensor. Typically, we then have a dense layer, and then we have our output layer. And then after we did a forward pass, and we have our classification, we compute the loss, we backpropagate the error, and we use the gradient to update these weights. Right? So again, if it would be better that this filter responds more strongly with this image, then we will increase the values of these filters here. Okay, now we will do this not for one filter. So here we have one filter. Instead of doing one filter, we'll take many filters. Say that this is our input image. So here we have two channel inputs. We have a width and a height. Again, we take a patch, like we take a 3x3 patch in this case, and we move that over the image. So we get multiple of these, actually 9 in this case. And we multiply each patch with the kernel. In this case, we have 3 kernels. So every single kernel gives us 1 output. We take 3 kernels here, so we have 3 output kernels. So we have 3 output values. And then we do this for, this gives us one part of the output. And then we move this patch over, or we move the filter over the image, over every patch. Each time gives us a new output. And at the end, we put everything together. And this is now our output feature map, right? So we started with width times height. And we end up with width minus the edges because we lose some pixels around the edges, times the number of filters that we've chosen. That's the design parameter. Okay. Now, we've already seen that we lose some information around the edges, right? Because if this is our input image, and we run a 3x3 filter around that, okay, the first filter will be this patch, right? This patch here. The second filter will be this patch. The third filter will be this patch, and so on. And so we go from a 5x5 image to a 3x3 output. So we lose some resolution in this operation. We can solve that by zero padding. We can put zeros all around the image, right? So we artificially increase our image. And if we do that, then we can, again, run our filter over this image. But now we end up with a 5x5 output image. Right? So by zero padding, we can maintain the original size of the image. Another thing you can do is, instead of taking one-by-one steps, we can also take longer steps or longer step lengths. We call that strides. So instead of going one by one, we can just take this 3x3 image, as this one, and then we jump over this one, we just ignore it, and then the next one will be this one. Right? This will effectively reduce the resolution a lot, right? So we started with 5x5 and we end up with a 2x2 output. A variation of this idea is called max pooling. So it's the same idea. We again do striding, but instead of taking the convolution of this patch with a filter, we simply take the maximum of all these values, and that will be our output. We can also take the average, but we've seen that in practice, taking the maximum tends to work better. So what this actually does, well, first of all, it drastically reduces the resolution of the images, which may be bad because we lose information. But on the other hand, if the resolution is quite high, we don't lose so much information. And it means that we have fewer ways to learn in the next layers, right? So it becomes easier to learn a problem, and it's less likely to start overfitting. So say we start with like 46 by 46. After convolution, this will be a 32 by 32 image if you take a 2x2 filter. So yeah, it helps with overfitting. Another thing it helps with is translation invariance. So what happens now if I have an object in this top corner here, right? If I do max pooling, then this object is now here, which is already relatively affecting more of the image. And if I now have a new convolutional layer, right, then this guy will affect a lot of the output of this layer. If I would not do that, if I would just have another image here, another output, and then this guy would only affect a small part of my output, right? Which means that the information that there is something here spreads very slowly through the network, and I would need a deeper network for this information to spread through the entire network. Why is this bad? Because then it depends on where something is in an image for me to recognize it, right? And if I use max pooling, this information spreads more quickly to the entire image. And if at the end this information is spread in the entire output of the next layer, right? So we do max pooling again, and then basically if something happens here, then it reaches the entire output, right? That means that it doesn't really matter where the object is in the image, right? It will still be recognized anywhere in the output, right? While in this case, this image will only be affected here and not there. That's translation invariance. And max pooling is very important to ensure this. It's simply a good idea because typically we cannot expect where something can be in an image. Sometimes this has information, sometimes it does not. And by having this invariance, it means we are more robust against detecting it's something, no matter where it is in the image. Okay, so now how do we build a convolutional neural net in practice? Well, first of all, we don't use one convolutional layer, we use many of them. And the idea there is that we can learn patterns at different levels of abstraction. We can use one convolutional layer which learns very local patterns, such as edges or lines or endpoints. And then the next convolutional layer can learn more abstract things, such as combinations of shapes or maybe circles or squares. And then the next layer will again learn more complex things. Also, we use max pooling layers again to increase translation invariance. And also make sure that you have sufficient filters in the first layer, right? Imagine you have a convolutional layer and then you only use 3 or 4 filters, then all the information has to pass through these 3 or 4 filters, which may destroy some information. So you want to have sufficient filters in the first layer. And in the deeper layers, you want to have increasingly more filters. So the rule of thumb is that you have to maintain the number of activations. That's the number of, well, that's the resolution of your image times the number of filters that you build. Otherwise, you can create a bottleneck and you lose information in the network. So if we draw this, say I have 100 by 100, sorry, input image, like that, and I have only 32 filters, then I end up with a tensor which is kind of wide but very narrow. Has few channels, right, like this. If after some max pooling layers, I have only like a 10 by 10 image left, output left, then I need many more filters to end up with the same number of activations, right? So my output looks like that. If maybe at the end I have only like a 3 by 3 output, that's perfectly possible. Then I need I need many more filters to have the same number of activations. So maybe here I have 128 filters or more. Right? So it's a good rule of thumb. Like if you design a neural network, start with sufficient filters in the first layers and look at how fast your resolution decreases and compensate that by adding more filters in a network. Right. So if you look at a real example, so here we have the Keras API. So I built a sequential model, so it's a sequential model without any branches or so on. My input shape is a 28 by 28 image, only one color, it's grayscale. And my first convolutional layer has 32 filters, and the filters are 3 by 3. And at the end, the output is passed through a rel activation function. Okay, after that convolution, I have a 2 by 2 max pooling, which will reduce dimensionality by 4. And because of that, I will increase the number of filters in the next layer to 64. Right? And then I have again the max pooling, and here I maintain the same 64 filters. That's a possible network that makes sense. If you look at what the output is, so now we have, so we started out with a 28 by 28 image. Now, because we didn't use zero padding, the output of the first convolutional layer is 28 by 28, but we have 32 filters, right? So now this already creates 312 parameters, 320 parameters, because we have a 3 by 3 filter plus one bias, that's 10 times 32 filters, it gives us 320 parameters. Max pooling will then halve my resolution in every dimension. So we get a 13 by 13 output, same number of filters. And in the next convolutional layer, we increase the number of filters to 64. We again lose some pixels at the edges and so on. So now we get 64 times 32 times 10 more or less parameters to learn. Then again, we have max pooling, so we again halve the resolution in every dimension. And at the end, we have one more convolution layer. So we end up with a 3 by 3 by 64. So this was 26 by 26 by 32, like that. And at the end, we have a 3 by 3, but we have 64 filters. Right, that's how our tensors change. And in total, we have about 56,000 parameters to learn. Now, we're still doing classifications, so we end up with, first of all, flattening, which means that we take our 3 by 3, we take our 3 by 3 output and we flatten it, so 3 by 3 by 46, or 64. So that's 564. So this becomes all flattened into one layer with 564, 576, sorry, nodes. And then we attach a dense layer of 64. And then we have 10 classes, so we have 10 output nodes, right? And this is densely connected all, right? All right, that's our entire image, our entire neural net. It looks like this. So total we have about 90,000 parameters to learn. If we run that, it takes about 5 minutes, we get 99% accuracy, right? Compared to, that's slightly better than the dense architecture we had before. But now let's try it on a real problem. So this is the cats versus dogs data set. So they're images of cats and dogs, which are actually quite different from each other. They're not nicely centered or anything. They're very different cats, very different dogs, different situations. They're all also different sizes, so we have to, and they're JPEGs. So first of all, we have to pre-process them. We do that by first of all taking a balanced subsample of 4,000 of these images, 2,000 for training, 1,000 validation, 1,000 for testing. We decode the JPEG images to floating point tensors. We then rescale them to 0,1, and we resize the images to 150 by 150, which means that sometimes the images are a bit squashed, but they're all the same size. Okay, now you don't have to do it yourself. Typically, you have a data generator that does this for you. In this case, we built a data generator from Keras. We rescale, we resize the images to 150 by 150, and this generator will give us batches of 20 images at a time. All right. So we built one data generator for the training set, and we built another one for the validation set, and another one for the test set. Now, our network has to be slightly more complicated because now we have, first of all, we have 150 by 150 input, right? And the problem is quite much harder, right? Because we have very different images. So we're going to add a new convolutional layer, and we also increase the number of filters in the last two layers to 128. And then we also add a larger dense layer at the end with 512 nodes. At the end, well, because it's a binary problem, you only need one output node. Okay, so this is our entire network. So we start off with having 150 by 150 images, and we end up all the way down here with 7 by 7 output times 128 filters. We flatten that, we push it to a dense layer, and then we have one output node. So in total, we have about 3.5 million parameters to learn. Training, same as usual. We use ARM as prop as the optimizer, quite small learning rate. Now we had batches of 20, and our image is, so our data set was about 2,000 images. So we can do mini batches of 20, and we do 100 mini batches per epoch. And we do 30 epochs in total. Right? If you do that, then we get this result. So yeah, it's not so good yet. If you look at the accuracy is sort of, well, it plateaus at about 70 to 75% accuracy. And we see that the accuracy, the training accuracy actually keeps improving. This means that our model is actually overfitting. So we can do different things now. One thing we can do is regularization. We can add dropouts, we can add L1, L2 loss, and so on. We can also generate more training data. That also helps. And later we'll also see how we can use meta learning. So instead of starting with randomized filters, we'll actually transfer filters which were learned beforehand on other data sets. Okay, first, how can we generate more data? So the principal idea here is that we take an existing image and we create many variations of that image. And we can do that by zooming in, like in this case, we have zoomed in and we have rotated the image a bit. Here we have rotated it a lot. Here we have flipped the image horizontally. Sometimes we like skew the image. And you can see that from an initial image, we can actually generate many new images, which have roughly the same cat in them, right? But they're different images, and they contribute different information to a network. Again, you can use a image data generator for that. So in this case, we create one where it's allowed to randomly rotate your images up to 40 degrees. It can shift the images left, right, up to 20%. It can shift them up, down 20%. It can shear the images, which means that you basically take an image and you kind of push one side of it. Like I gotta push that direction. Like slant the image. So that also gives you a new image up to 20 degrees, 0.2 degrees. You can also zoom in up to 20%. You can do horizontal flips. And then, of course, because sometimes you create empty space here, you have to fill it up. And in this case, the fill mode is nearest, so you take the nearest pixel, you just kind of copy that all the way down. Right? So if you look at our generated images, you can see this happening also. So for instance, here we can see that this image was zoomed in, and this was empty space. So kind of we filled this in by just copying the pixel all the way down here, right? Yeah, same here. It's quite noticeable here. There's like empty space here because we shifted to the left, and then we kind of fill this in by copying the pixels here. Also here we can see it, and here as well, right? So yeah, that's how we create many images from a single image. Next to data augmentation, we also confront our overfitting by adding dropouts before our dense layer, right? So yeah, we have a same network, and then after flattening, we add dropout with 0.5 dropout to break any patterns that we learned by accident. Yeah, and it will also help in fighting overfitting. If you look at the results, we can see that it actually worked very well. So our combination of having more data and having dropout actually makes our model not overfit anymore. Right? If you look at the training accuracy, it's now going up to 80%, which is like 5% better as before. And it's not overfitting anymore, right? So we actually have some more room here. So we could actually train this for longer and we probably get a little bit better. Okay. Now, are we really sure that the model is not overfitting or that it's not learning some biases in the data? Now, to understand it better, we can interpret the model. We can look at the kind of activations that the filters are generating. And if those activations kind of look interesting, then it probably means that the model is picking up on interesting facts, well, interesting patterns in the data, right? So we can take an image, we can push it to the network, and we can see how the output, the feature maps look like. And maybe that learns us, that teaches us something about what the network is doing. Right, so we take a specific test image and we push to the network and we will observe the outputs. Okay. So the feature maps we generate, they look quite different. So the first ones are 148 by 148 by 32. So here we have 32 filters, yeah, so 32 channels. And the next convolution, they're smaller. They're only 72 by 72, but there are more of them. And if you go deeper, we go all the way down to like 7 by 7, but then we have like 128 of them. Okay. So let's look at them. So how can we look at them? Different ways of doing that. So in principle, you could just take a trained model. So we have multiple convolutional layers, right? And then we flatten that, and then we have our dense layer, and then we have our output. Right, so this is kind of our network. So we can like train this and then push a new image here through the network. And then maybe chop off some part and then look at the output. Another way we can do this is create a model in which the layers are different outputs, right? So instead of having only this output, we also output all these convolutional layers, right? These become outputs of our network, right? Which means that now we can train it, we can push the network, and then we can request the feature maps here as outputs of a network. Right? So here we have our inputs, image, this guy, right? We predict this, and then we look at all the outputs, and then we plot them. Right? So this is what happens for the first layer here, right? If you look at filter 2, this layer had, I think, 32 filters. If you look at filter 2, this is what comes out, right? So this is our input image, this cat. And we see that this filter kind of responds to vertical or slightly diagonal lines, right? So like this ear and corner of this eyes and this nose, the bridge of the nose, and so on. So this filter is actually sort of an edge detector. If you look at another filter, this is filter number 16. This one, well, responds quite strongly to like circles or round shapes in the image. So in this case, it very clearly highlights the eyes of the cat. We can also take the same filter and look at the response for a different image. Say, what happens if we input a dog? Well, then again, it sort of detects round shapes. Now it detects leaves in the background or the nose or maybe the eyes here. But you can see that the response is quite different for different input images. And that's exactly what we want. We want these filters to react differently to different inputs because then we can learn how the images are different and we can use that for classification. Okay, so these were just two of the filters. We have many more. So in the first layer, we had 32 of these filters. And a lot of them are edge detectors. So we can see they detect all kinds of edges, horizontals or verticals and so on. This is more horizontal. This one is more vertical. Some of these filters, they don't respond at all because they may respond to dogs maybe or to other cats, but to this cat, it does not respond at all. And some filters, they kind of make, well, they let the image through mostly unchanged. And that's also good because that kind of allows the information to go deeper into the network. Right, so this is the first layer. Then we have max pooling, and then we have a next layer. So now the resolution is much smaller, right? So here we had 150 by 150. Here we are left with 75 by 75. And we can already see that well, these ones are much stronger, right? So these filters, they strongly react to diagonal lines. This one more to vertical lines. This one reacts to eyes very clearly. Some react to ears more strongly, and so on. But today, these filters are responding more or less to larger patterns in the data. If you go to 5, we see filters that strongly react to actually concepts like ears here, or it could be nose or the eyes here. Right? If you go even deeper, then, well, the resolution gets lower and lower. So here we only have maybe 13 by 13 left. And we can see some of them very strongly react to the ears. But of course, the deeper you go, the less easy it is to just recognize things. We just hope that they respond strongly to certain types of images and not to others. We can also see that some filters don't respond at all. Well, these filters don't respond to this cat. They may respond to other images. And in fact, if we give a dog as the input, then we can see that these are the same filters, but the outputs are very different. This is the output for a cat. This is the output for a dog image. Right? So we can see that they behave quite differently. This one detects the eyes, the ears here. This one does not detect that at all. Right? So it doesn't respond in the same way at all. Right? Probably because in this image there are no clear ears visible. Oh, maybe there are, but yeah, it doesn't respond so much here. Not in this one. Right, this is what we want. We want these filters to respond very differently to different images, because then we can distinguish between them. All right, so what we saw here is that these convolutional networks, they learn spatial hierarchies. We get our image of a cat as input. The first layers, they detect lines, like diagonal lines, horizontal lines. And then the deeper layers, they learn more complex abstractions, such as eyes or noses or ears. And at the end, we hope that from these things, we can then recognize this object as a cat. We can also visualize the filters. Now, the filters themselves are not interesting because they are just 3 by 3 images, but we can see which input images they respond most strongly to, right? So, for instance, if we have here a filter that seems to respond to ears, we can see which input images it responds most strongly to, and then looking at the input image, we may learn something about what this filter is actually responding to. Right? So it's kind of the other way around. In this case, the previous case, we took an image and we look at the response. In this case, we want to take one specific filter, and we want to design the input so that it activates maximally, right? And the process to do this is called gradient descent in input space. Basically, what you do is you take a specific filter, which is somewhere maybe in your last layer, right? There's a filter here. And this goes through a dense layer, and then there's like one output, like cat or dog. So hopefully it's a 1 if it's a cat, right? Okay. And then we start out with just a random input image. And we just feed forward that to the network. And this will respond, this filter will respond in a certain way to this random image. And what we then do is we compute the gradient of the loss in terms of, our loss in this case is the output of this specific filter, right? So we hope that it responds strongly. If it doesn't, we have a loss, and we will see how, we compute the gradient of this loss in terms of the model input. Right? And so after we compute the gradient, we know which pixel values we need to update. Right? So this is our input image, and we update this input image with certain step size according to the gradient. So we will increase some pixel values, decrease some other pixel values. And we do this over many iterations until we find an input image which creates a very strong response from this filter. Right? Okay, so if we do that, so this is for the second convolutional layer in our cat versus dog classifier. We can see that here's a filter. So here we have 150 by 150, right? Because we can reverse engineer the input image. So this filter responds to input images which have short horizontal lines. This one responds to the diagonal lines. This one responds to blue pixels. This one responds to red pixels and so on, right? So we can already see that some filters react strongly for some patterns. This one is more like wavy and so on, right? For the last convolutional layer, we can see that some filters are really focusing on the center of the image because apparently that's more interesting. We can see some of them have some patterns, like this could be an eye, or yeah, some color shapes that occur in the images. Right? So They're not super easy to recognize, but at least it seems that the models are paying attention to certain aspects of the image, which makes sense. Now, this was only done for 2,000 images, so that's not so much data. What if we use for much larger network for much more data? So for that, we can use the VGG16 network, which is a much deeper network. So it starts with 2 blocks of 2 convolutional layers, each interspersed with max pooling, and then 3 blocks of 3 convolutional layers. And this is trained on the ImageNet dataset, which is a very large dataset with hundreds of classes. If you look at those filters, we can see that for layer 5, that's the first one of these blocks of 3. We see that there's a filter here that responds to like dots or holes in the image. This is a filter that responds to like horizontal lines or waves in the image. This is for the first layer. We can see the first layer looks at colors, looks at horizontal lines, vertical lines, diagonal lines, sometimes very fine lines, sometimes very coarse lines. Some look at the edges, and so on, right? So we can see the first layer finds very local patterns. The second block of convolutional layers, here we can see more fine textures. Like this could be like different textures occurring in images, like vertical lines, horizontal lines, lines interspersed with holes. We have these kind of crevices, and so on. Right? So this looks like different types of textures. This could be like a skin or something else, right? If you look at the third block here, we have more natural textures already. So we see maybe these are like wavy lines. These look like holes. Right, so we can see more and more patterns that kind of resonate with us. Right? Here we have these, I don't know what this is, yeah, like circles happening in the images and so on. And the fourth block, here we already see things like eyes. Right? This really looks like an eye. And we have here like scales or like waves or other patterns, right? So we can see that it kind of has learned to respond to certain patterns which occur often in real-world images. So that's one thing we can do. Another thing we can do is to visualize the class activation. That's a whole different thing. So here, in this case, we take a particular image and we want to see which part of the image the model is paying attention to while it's classifying it. And the way we do that is we take a convolutional layer, for instance, the last one here, and we can pass many images of the same class, like the class dog, through here. Right? And every time these filters will respond to that in certain ways. These are, for instance, different filters, and they respond differently for different inputs. Right? So for this input, the first filter reacts more here, the other one more there. So if you compare this to what we had before, our cat images, so here we have all the filters in our last convolution layer, right? And you can see they all react differently to the input image of a cat, right? Same here. Here, these filters respond differently to this image, right? Now, if we give many images of dogs, we can see how often, for instance, this particular filter responds to seeing a dog. Right? So if this filter here responds strongly to lots of dogs, this filter tells us something about whether there's a dog in the image, right? And we can then increase the weight of that filter, right? So the idea is that we learn a weight for every filter according to whether or not that filter corresponds strongly towards seeing a dog. Right? And we can do that by computing the gradient of the output versus the output of the image. And when we've learned these weights, we can sum them up and then end up with what we call a class activation map. And this should indicate where all these filters together are looking at when they make a classification. So if you would translate this to our cat versus dog situation here, we have different filters. Oops. Like this filter here, this filter here, this filter here. And so say we have this filter here, which does not respond strongly to this cat. This one here seems to correspond more strongly to a cat. So if we see over multiple images of cats that this one does not respond to cats, we can give it a low weight, like 0.1. If we see that this filter always responds strongly to cats, we can give it a higher weight, like 0.9. And then we learn a weight for every single filter. And then when we classify a new image of a cat, what we do is we take all the activations, we weight them by the learned weights, and then we basically sum up, well, we take the weighted sum of all the activations, which gives us a new activation that will hopefully light up in certain parts which are interesting. Okay. So for a real world example, let's look at this elephant here. So we hope that the model will look at interesting parts like the head or the body, but not the sky or the grass. Right? So if you want to do that, so our input size here is 224 by 224. So we have, this is the input size that VG was trained on. So if we take a new input image of the elephants here, what we have to do is first to pre-process it. Some things we can do ourselves, like rescaling. Other things are less obvious, but we can ask for the preprocessing function that was used for VGG, right? And then we can input our image through the same functions, so we will preprocess it in the same way as VGG was trained for. And just to check whether that gives us a good prediction, so in this case, our image is classified as, let's show what this is. So it predicts with 9%, 91% confidence that this is an African elephant. And the corresponding activation map looks like this. So it's looking at this part of the image mostly. This is the sum of all the filters, right? And if you then superimpose that on the image, we can see that the model is looking at basically the head of this baby elephant here, also at the body more, and also a bit to the other elephant here. Right, so this is basically the sum of all the activations of the filters that would respond strongly to elephants. And it teaches us that this model has learned something useful. Right? It's paying attention to the elephants and not to the grass or the sky. All right. And one more thing. So instead of, well, we've seen here that there exist already networks that have been trained on recognizing real-world images, like ImageNet here. Now, instead of, if you have a new classification problem for images, instead of starting with random filters, we could actually start with the pre-trained filters, which already have learned how to recognize interesting patterns in real data. That's called pre-training, right? So the idea is that we take an existing model that has been pre-trained on another, typically larger and hopefully similar data set. Of course, this model was trained for predicting something else, so we're not interested in that. So we remove the last layers, and then we add new layers to make the prediction that we want. But we don't want to touch these the convolutional base, right? The filters. We want to use the same filters. So for that, we freeze all of these weights, and then we can train this network on our own new data. For instance, the cats and the dogs. And we hope that the same filters that we learned before are also useful for our new task. This is called transfer learning. So we transfer from one task to a new task. And this is only one kind of meta learning. So meta learning can be much more general. You can transfer from many tasks to a new task, or you can do never-ending learning where you just go from task to task to task and you learn what to transfer from one task to the other. It's a very interesting research domain. In this case, we just do a transfer from one task to a new task. So, okay, let's do that. So we start off with VGG, 16 again. We use the same weights as were trained on ImageNet. We remove the top part, the dense layers, and we reshape the input to 150 by 150 by 3 because that's the size of our cats and dog images. Okay, so our new network looks like this. So input 150 by 150 by 3. Then we have all our convolutional layers, which we just keep as they are. And then we can do different things. So one thing we can do is just keep this and keep this frozen. We take our input images, we push them to the network. They come out here as 4 by 4 by 512 tensors. And we can then flatten them and give them to another model. Right? So just push all the images to the network, and we take the output basically as a new featurization of the image, a new representation of the image. And then we can pass those to a new neural net or any other algorithm. We can also pass the new representation to a support vector machine, for instance. Right? That's one thing we can do. Another thing we can do is end-to-end tuning. So here we take, again, our pre-trained network. We remove the head, and we add some new layers, new dense layers. And then we retrain the whole thing end-to-end. Right? So the only thing that we do here is that instead of starting from random weights, we start from initialized weights, but we will adapt them to the new task. And this you can only do when you have sufficient data. Right? So the first thing, the feature extraction, you can do even if you have little data. End-to-end tuning is quite a bit more expensive, so you need a lot more data to do that. And then the way between is called fine-tuning. So here we keep most of the convolutional base frozen, except for typically the last few layers. Why? Because the last few layers are typically already like geared towards the previous prediction we want to make. It learns some high-level abstractions which were useful for our previous tasks and which may not be useful for our new task. So we unfreeze the last convolutional layers. We then add new dense layers at the end, and then we train the new layers and the last unfrozen layers. Right. So let's see how that works. So the first ID, just fast feature extraction, right? So that's the first ID here. So we do that by with data generator. We take a convolutional base and we basically push all our inputs to the convolutional base with the predict function. this gives us our new representation of the images, and we can then give that new representation as input for a new neural net, or you can also replace this with a supervector machine, for instance, in which case you would have to flatten this, but you can do that. We also add dropout here for overfitting. And if we do that, we get 90% accuracy, which is about 5%, no, 10% better than the previous model, which is pretty good, right? So actually, like taking a model learned on a previous problem and then using the same weights actually gives us very good performance with very few data points. This does not always work. Right? So there's a nice paper by Yosinski, which is in the reading list from 2014, I think, where he shows that sometimes it works, sometimes it doesn't work. It's really not sure when it does and when it doesn't work. It has to do with how similar your new task is to your previous task and so on. Right? But in this case, it works nicely. We do see that there is a little bit of overfitting, so we can still improve that. And one thing we can do is just give it more data. So we can have the same solution again, but now with data augmentation. So in this case, we don't have the two models, so just make one big model with the convolutional base. And because we're going to train this thing, we're going to train this new dense layer here, we have to explicitly freeze the convolutional base. And we can do that with the trainable attribute. If you set that to false, then the model will not tune the parameters of the convolutional base. If you look at the model, we can see here there's a VGG model, and we can see that in total it has about 17 million parameters, but about 50 million of those are fixed, are frozen. We don't touch them, and only the remaining 2 million we train. So we build our training generator. And if we do that, then we see that again, we get about 90% accuracy, but we see that there's still the same performance in terms of accuracy, but there's less overfitting happening, which is a good thing. It may generalize better than the previous model. And last thing we can do is fine tuning. So here we keep everything frozen except for the last block of the convolutional layers. So yeah, so if you remember our VGG model, right? So we keep all of these frozen except for the last block here. We unfreeze that, and we want to learn those, well, we want to tune those weights, but starting from their original setting that was already learned. Okay, so visually, these guys are all frozen. This one is unfrozen, so you want to fine tune them, and then this is our dense layer and the output layer, which we have to learn from scratch. Yeah, so one thing is that if you do this, always use a very small learning rate. Why? Because you may easily unlearn the features that you have here, the filters that you have here. Because in the beginning you have like almost random weights here, and you have large gradients, and so you may easily destroy the information that's in your filters here. This is called catastrophic forgetting. It means that you have one task and you want to transfer to a new task, but fine-tuning on the new task destroys all the information in your previous model, and you want to avoid that. There's different ways of doing that, but important here is that you have a very small learning rate for avoiding that as much as possible. And if we do that, then we get 95% accuracy, so it's 5% better. It's great. It overfits a little bit, not too much. And yeah, it's a bit noisy. So if you're bothered by that and it's hard to interpret things, you can just smooth it over with a smoothing function like a burning average. We can see here that our model is very stable. It may overfit still a little bit, but it's It's very stable. Now the proof is in the pudding. This was on our validation set, so let's break out our test set and evaluate on that. And we see that on the test set we also get 94% accuracy. So that's consistent with what we had before. Okay, great. So we've learned that convolutional nets are ideal for attacking all kinds of visual classification problems. And it's not really limited to visual. It's actually useful for any type of contextual information. It also works for like sounds or video. It even helps for text because there's a context that you wanted to keep into account. And they kind of learn efficiently on image data because they learn a hierarchy of patterns. They first learn simple patterns and then they construct more hierarchical patterns on top of that. And this is a very clever technique. It's basically called compositionality. You kind of break down a hard problem into simpler problems, and this also makes learning much easier. Right? And the second thing is that because you learn these composable patterns, they also transfer better. So you can actually use this for transfer learning. Another nice thing is we have techniques to introspect the algorithm, the model, to see whether it has learned something useful. We can use the augmentation to fight overfitting. And like I said before, they transfer typically quite nicely. So you can actually solve problems which have very little image data by transferring the filters that you've learned from previous problems in different ways. Okay, that's it. I hope you enjoyed the lecture and see you next time.